Over the next several videos, we're going to be looking at reactions. Whoops, purple's not a great color. Looking at reactions of aldehydes and ketones. There's quite a bit of material in this portion of the chapter. It could easily be its own chapter. And so I'm going to start out with some review, and then we'll move into some new material. There's really not too many different mechanisms. There's just a lot of possibilities within the mechanisms. So what I thought we'd do to begin with is do some previous reactions. There's one I'm sneaking in, but for the most part, these are all previous. So these are all reactions we've done in the past. One is you can oxidize aldehydes. Right, and so if you start with an aldehyde and you put in an oxidizing agent, you will get a carboxylic acid. Now, of course, if the oxidizing agent is basic, you really won't get the carboxylic acid. You'll get its conjugate base, right? You'll get the carboxylate ion. And then you'd have to add acid to get to the carboxylic acid. But for the most part, people will just say it oxidizes to carboxylic acids. You don't need to know the mechanism. You don't need to know anything. You just need to know that aldehydes oxidize to carboxylic acids. In addition, you can't oxidize a ketone. You can only oxidize an aldehyde. Next is there are some reduction reactions. You can reduce to different things. So the first thing is you can reduce to alcohols. And again, we've done these in reverse several times, right? So if you take aldehyde and you reduce it, the most common reducing agent will be sodium borohydride, or you might see lithium aluminum hydride, but those are the most common ones that you'll see. What you're going to get out of that is a primary alcohol, right? It's the reverse. In the previous chapter, we took primary alcohols and oxidized them to aldehydes. Now we're taking aldehydes and reducing them to primary alcohols. If you start with a ketone and you reduce it, you're going to end up with, oops, not an O, typo. You're going to end up with a secondary alcohol, right? And we did these in reverse in the previous section, where we took a secondary alcohol and oxidized it to a ketone. It means you can take a ketone and reduce it into a secondary alcohol. So those are reducing to aldehydes or ketone, reducing aldehydes and ketones to alcohols. You can also reduce them to alkanes. Now we saw this in the aromatic chapter. And so if you start with a ketone or an aldehyde, I'm just going to say on here H or R prime, right? So it could be an aldehyde or a ketone. We saw in the last chapter, if you took zinc and mercury, in the presence of HCl, you could reduce that to H or R, right? We did that with the side chain. Remember we took the Friedel-Crafts and we said with zinc, mercury, amalgam, and HCl, you could convert that to the alkane. Well, it doesn't just work with aromatic ketones. You could do it with any ketone. When you use that under acidic conditions, that's called the Clemmensen reduction. And then they made up a way, just in case you don't want to be under acidic conditions, that you can do this under basic conditions. And that's called the Wolff-Kishner reduction. And in the Wolff-Kishner reduction, you use a molecule that looks like this. It's not going to be written out like that. They're just going to write NH2, NH2, or sometimes they'll write it as N2H4. or sometimes they'll go NH2, NH2. All of these things are the same, right? They're all the same thing. Under basic conditions, so under hydroxide, you'll get the same product. So both of those conditions give the same product. It's just a matter of which one you want to be under, acidic conditions or basic conditions. So this is the new one that I snuck in, right? So we didn't really see the Wolff-Kishner one before. And that molecule, I should tell you, I could also tell you, NH2 is the name hydrazine. All right, so you can use that as a reaction in order to get it to go. So those are some older reactions that at least hopefully you saw somewhat of. And so what I'm going to start on next is the main category of reactions for the next bulk of the chapter. And that's going to be nucleophilic addition reactions. I'm going to just start out by looking at the general reaction, and then we'll get to all the specific ones, of which there are many. First of all, when you do this, this is kind of a combination. You've already seen this mechanism because we've done it. I just never gave you the name of it before. You're going to take a nucleophile and add it across a double bond. Now, we did this in the past. We had alkenes and we had electrophiles, right? We had, let's just do, we did them as XYs, right? We had electrophiles. And this donated electrons, right? But when we were done, we got to X and Y adding across. We went from sp2 to sp3, right? We changed the hybridization. And so we added things on, but we used an electrophile. In these reactions, we're going to have C double bond O, and we're going to take not an electrophile, but we're going to use a nucleophile because that's what's going to be attracted to that partially positive carbon. So it's similar to the reaction we did in the past, yet it is different. So there's two conditions you can do this under. You can use a weak nucleophile. But if you do that, you typically have to have an acid catalyst. I know that seems weird to think that you need an acid catalyst. Why doesn't the acid just react with the nucleophile? And honestly, it's kind of a tough balance on some of these reactions to get the pH just right to get the product that you want. If you make it too acidic, the acid does just react with the nucleophile, and that's the end of that. If it's not acidic enough, you can't get it to go because the nucleophile won't attack the carbonyl. So how does an acid help? How does this catalyst help? If you look at an aldehyde or a ketone, right? If that's H, it's an aldehyde. If it's R, it's a ketone. We know that it has resonance. Right? But this is the major contributor because A, it has no separation of charge, and B, it obeys the octet rule. And so even though this carbon has partial positive, it's not really as much positive as when you look at the minor contributor. So you can do things to make that carbon even more positive, to make it so a nucleophile would be even more attracted. And one of the things you can do is add acid. Because if I add acid to this, and I protonate that oxygen, I'm just going to put a line and assume that you're going to know that it's to it H or R. It's just it's going to be long to always draw that. And so when we get to this thing has resonance also. I could take the lone pair of electrons and go up to the oxygen. And when I do that, it's true this still has an incomplete octet. And this is still the major contributor. But this is better. This one is more stable than this one. If I compare these, this one has no separation of charge. right? This one has a separation of charge. It takes energy to pull that positive and negative away. So this is, even though it's not the major contributor, it has more character. It's more stable than the one above. So even though it's the minor contributor, it adds significant positive character to the carbon. And if the carbon is more positive, then a nucleophile is going to be more attracted to it. Remember, a nucleophile is seeking positive charge, right? So if something has more positive, the nucleophile will be more attracted to it. So in an acid catalyzed situation, what you're really doing is making that carbon more reactive. And so the whole slew of it, the whole shebang of it would look kind of like this. If I were to take my carbonyl and react it with acid, of course, these are acid-base reactions, so they are all reversible. I would have this, which is in resonance, right? This is in resonance with this. And then if I took my nucleophile, I'm going to just put a hydrogen on my nucleophile. It makes it look a little weird, but when you have it under acid conditions, it's not uncommon for that to be true. It doesn't always have to be on there, but I'll show you I actually am cheating and I want it on there for a reason. The nucleophile is going to attack that carbon. If I do that, I'd end up with this as my product, right? I'm just showing it attacking the one possibility. Once I get to there, I can do two things. I can just have whatever, say this is in water and that, right? I could just have water come along, right, and pull off that hydrogen, and I could get to COH nucleophile, right? I could have that plus H3O back, right? So the hydrogen comes back off, so it's just a catalyst. So that's one possibility. So I could get to this product. Second way I could go, though, is once I have this, this oxygen could pull that hydrogen off. And so if that happens, then I'm going to end up with OHH plus my nucleophile. And my nucleophile will no longer be positive, it have electrons. And what's possible now is OH plus could, OH2 plus could be a good leaving group. And so these electrons can come in and that can go off. And of course, these are all reversible, right? And so I could end up with water and a double bond to whatever the nucleophile is. In this case, it would have a positive, but I'm not meaning to, I'm just following the electrons for this. When we get into examples, you'll see they won't all have positives. And so you can end up with a different kind of product that we haven't seen before. When water leaves, that's called dehydration. And lots of times you'll see over an arrow minus H2O. The minus is telling you it's leaving. Right? And so don't think it means you're adding water. It's telling you water is leaving. So we're going to come back and do real examples with real nucleophiles, but that's under acidic conditions. The second one you could do is if you have a strong nucleophile. If you have a strong nucleophile, you typically don't need a catalyst. And this is the one that kind of we've seen already. If you take this with a strong nucleophile, which typically have negative charges, it will attack and you'd get to this. And then remember in the second step, this is like adding a Grignard. In the second step, you add acid. And you could get to that product. However, it could also, with acid, can also get to a similar product as the previous one. And so you're either going to just add it and get an OH in the nucleophile on it, or sometimes it dehydrates. And I'm going to show you the exact ones that do which ones do what and when you have to worry about it. So I was just trying to show you in general the mechanism and what we're going to be doing. And so in the next few reactions, I'll put the actual structure of the nucleophile in, and that should hopefully make it a little clearer. I know it's abstract when I just do the general ones. And so let's do one that you're familiar with. Let's call this number 2, and let's start out with the easier one and start out with what things could be strong nucleophiles, right? And so the first one is a Grignard. Remember in our MGX, these are called organometallic compounds because they have carbon bonded to a metal. Remember, metals have very low electronegativity. Carbon is actually more electronegative, so the carbon is negative and the metal is positive. So this kind of acts as, or minus, right? Kind of acts as a carbanion. They won't write it as a free carbanion, but that's what you can think of it as. So the general reaction, oops, I'll do it as I. The general reaction, and we've already seen this, right? If you take an aldehyde or a ketone and you react it with this, these electrons come here and these go off onto the oxygen. And then in the second step, you add acid. And you're going to end up with an alcohol. And specifically, right, if we want to do these specifically, if you start out with an aldehyde and you react it with a Grignard, second step acid, you're going to end up making a secondary alcohol. And if you start with a ketone, I'm using primes and double primes because the R's don't all have to be the same. And if you add a second step of alcohol, of acid, sorry, you're going to end up with a tertiary alcohol. Right. So in this specific chapter on aldehydes and ketones, when you react an aldehyde with a Grignard, you form a secondary alcohol. And when you take a ketone, you'll end up with a tertiary alcohol. And so if you want an example with actual structures, if we were to take something like cyclohexanone and react it with methyl magnesium bromide and add a second step of acid, what would we get as a product? You can pause and predict your product, but these are going to attack, right? So you're going to end up getting O, which will eventually get protonated, and then you're going to have CH3. Right, and so that would be your product. And that would be a tertiary alcohol because you're starting out with a ketone. So that's one that you've already seen. We've done this under the alcohol chapter, but now the mechanism falls under this new nucleophilic addition language. The second type of thing you could add are acetylides. Now, you might not remember what is an acetylide. It's been a while, right? An acetylide is the conjugate base of a terminal alkyne. Remember, terminal alkynes are somewhat acidic. You need to use a strong base, but you can get that, get it to react. And so our general reaction would be, oops, let's get rid of that. Our general reaction would be if we started with a carbonyl and we react it with an acetylide, we'd get to this. And then if we add acid next, we'd get the OH, right? We'd pick up that, and we'd have, I'm drawing it straight down because remember it has 180-degree bond angles, right? And this is actually an ine all, right? We got an alkyne and an alcohol. And just to refresh your memory, how would we make this acetylide? We'd start with a terminal alkyne and react it with a strong base, something like amide would do it. And so you can make the acetylide from the terminal alkyne, and you would end up with this ine-all as a product. And so let's do a specific example. Let's again just pick on cyclohexanone, but if I showed you cyclohexanone and I said 1, we're going to react it with CH3, and then second step add acid, what would you get as a product? You can pause if you want, right? This is going to attack and go out. So it's going to end up with a single bond, C, triple bond C to CH3 would be here. And then when you add the acid, you'd protonate that oxygen. So you'd end up with this ine-all as a product. So those are pretty straightforward. I don't think that those are necessarily too bad. The next one that you could add, I'm going to make it seem easier. I'm just going to call them hydrides. I'm really not telling you the whole picture with these though. This is really when you're using sodium borohydride or lithium aluminum hydride. You can think of both of these things as really just a source of hydride. You remember what hydride is. It's ending in IDE, so it's a negative ion. It's just hydrogen with a negative charge, right? It has 2 electrons and a negative charge. And sodium borohydride and lithium aluminum hydride are isoelectronic. Their electron structure is exactly the same. So you'd have sodium, that's a cation, and then you have the boron attached to 4 hydrogens, and boron would in this case have a negative charge because boron's in group 13 or 3. It only has 3 valence electrons, so when you give it 4, it's negatively charged. And you can think about this piece of it as kind of being in equilibrium with the hydride and boron only having the 3, right? It's really kind of the Lewis product of taking this Lewis acid, BH3 is the Lewis acid and hydride is the Lewis space, right? You could put those electrons on there. But what we're thinking about both of these is just really being a source of hydride. And so now if you have a carbonyl and you react it with hydride, it doesn't really react this simply. There's a whole slew of things, but this is kind of nice to just show it this way. You get the hydrogen added, and then in the second step, if you add acid, you can protonate there. And that's how it actually reduces the carbonyl to alcohols. So it really follows nucleophilic addition using hydride. And so an example would be if we had something like this, and we're reacting this with sodium borohydride. You can just think about this thing as being H minus, and then second step, we'd need to add acid. That would become OH, and you would add another hydrogen here, right? It would have 1, now it will have 2. So aldehyde will be reduced to a primary alcohol. If you start with a ketone, it's going to get reduced to a secondary alcohol. The last reaction in this little category is if you were to add cyanide ions. Right? And so the general reaction. It's really the carbon end that has the negative charge out of this when you draw the cyanide ion. It's not the nitrogen that attacks, even though when they draw it, they write Cn minus there. It's actually the carbon that's negative. And so this is going to attack. And then the same thing, add acid as a second step. So protonate. Oops, I drew that wrong. Sorry, got carried away. This will protonate, right? And you'll end up with the alcohol there and then the cyanide here. This thing, when you have an OH and a cyanide on the same molecule, this is actually called a cyanohydrin. And historically, cyanohydrins were important because of a reaction that we don't really know yet. But you can take cyano groups, and if you throw them in with aqueous acid, they actually turn into carboxylic acids. When you react them with a aqueous acid, it's called hydrolysis. And so you can hydrolyze cyano groups into carboxylic acids. And so why was this important? If you think about those of you who've had biology, building blocks of proteins are alpha amino acids, right? And so what that means is this is the acid, this is the alpha. So this on the alpha, you have an amine group, an amino group, but this is the carboxylic acid of an alpha amino acid. Whatever's over here are all the different amino acids. So they were trying to historically make alpha amino acids. And so one of the ways they could do that is by starting with an aldehyde or a ketone, turning it into a cyanohydrin, and then throwing in a lot of aqueous acid. And what you would get out of that would be alpha hydroxy amino acid, and then go through a bunch of substitutions. And then you could, by substitution, convert this to an NH2. And that's how they were making alpha amino acids. So this reaction kind of has some kick to it and has been around for quite a long time. You can do this reaction also by using the weaker nucleophile under acidic conditions. So you can also use HCN in place of CN minus, and you'll get the same thing, because now if you put in HCN, you can protonate this and get cyanide, and now the cyanide will really attack here. And so you can get the cyanohydrin this way as well. And so let's just do an example with not an R, putting some R's in there. So if we had something like, let's do it in line structure. If we had butanone, and I told you we're going to react it with HCN, your product should be OHCN, right? It's just going to add across there. And if you wanted to draw the CN down underneath, it would make no difference. You could also show that as CN like this, right? But it's to this carbon. I'm not implying any kind of stereochemistry to it. If it creates something that's chiral, as this does, you'd get a pair of enantiomers. Remember, if you start with achiral, that's optically inactive. You got to get a product that is optically inactive. We're not going to really worry about that. There's so much on here. We can come back to those details. So I'm going to stop this video. That's really the end of the strong nucleophiles. The next one will be on weak nucleophiles. And that might even go over 2 videos. We'll see how long it ends up being. And then we'll have to do when you have an alpha beta unsaturated carbonyl, that's also in this chapter. But that's enough for this video.